The next example is the construction of a semimonad or a monad, which looks like this. For any functor g, we take the tuple of a and g of a, and that is the new type constructor f. And we will now show that in general, you can define a semimonad for f, and if g is unit, that is, there's no g here, just a, that's the identity functor, and that's a full monad. There's no other way that you can get a full monad out of this construction. So how do we show this? First of all, we need to define a functor instance for this, and then we will define a semimonad instance. To define the functor instance, we need to produce an implicit value of type functor of f. But actually f is not defined as a type constructor, because we have this arbitrary functor g. So we cannot define a type constructor f without first defining a g directly. So instead of defining it directly, we use the kind projector, and so then this syntax will represent the type constructor that takes a type x and produces the type of tuple x and g of x. And so we will have to keep writing this type expression instead of f, which is okay if you don't have to do it far too many times. Later we'll see we can a little cut down on this repetition. So the functor instance for this type constructor is straightforward. We need to implement the function map, which takes an fa, which is a on g of a. It takes also a function f, which is an arbitrary function of arbitrary type, a to b. And we need to produce a tuple of b and g of b. So to do that is relatively straightforward and unambiguous. We use the fact that g is already a functor. So g already has a map function of its own. We use the type constraint here, type class constraint, to say that g is a functor. And we have imported the syntax for functors, and so now we can just say g ga dot map. So that's what we do here, using the functor map from the functor g. So how do we produce a tuple of b and g of b? Well, obviously we have a tuple of a and g of a. So this is this tuple. We destructure it using the match expression. Obviously we need to use the function f to produce anything that has b in it, because there's no other way to get any kind of b except by using f. So we call f on a to get a value of type b here, and we do a ga.mapf, and that gets us gb. So that's easy enough. Now, how do we define a semimonad? Now, this is a little more involved. So again, we assume that this is a functor, and we are going to produce a value of type semimonad of this type constructor expression. And that's going to be the implicit value, but this value is parameterized by g, so we need to make it a def. So the function we need to define for the semimonad is flatMap. So how do we define flatMap? Well, we have an arbitrary function of type f, sorry, of type a to B and GB. We have a tuple AGA, and we need to obtain BGB. So let's think about how that function could be defined. And to get intuition about it, let's remember that monads represent some kind of computational context or effect that accompanies a value. And so here, obviously, we have a value of type A and also a value of type G of A, which we could consider to be the effect or the computational context of the value A. So just intuitively. Now, we have the initial value that has its own effect. That's the first one. And also we have, when we apply f to anything, we will get another g of b, which is a second effect. Now, clearly, these g of a and g of b, they are arbitrary functors. We cannot combine them. So usually a monad would combine the two effects into one. So for instance, if this were just the reader monad, that would be a tuple of A and W, and here would be a tuple of B and some other W, and we will just combine this W and that W using the semigroup. But here we don't have a semigroup. So G is an arbitrary functor. There's no way for us to combine two values of type G of B, say. We could try to map f over this, but then we'll have a G of B, and we can't combine that G of B together. So we have to discard one of the effects, basically. That's the basic reason why this cannot be a full monad. Usually when you discard effects, that's a red flag in terms of having a full monad. A full monad doesn't discard the two effects, it combines them in a monoidal fashion. Semigroup combination can discard, but monoid combination cannot discard. If you cannot define a monoid when you define your binary operation that discards one of the arguments. That will be not a lawful monoid because it would not have an identity value, because you could not combine identity and x to get x when x is discarded. So you're not allowed to discard if you want to have a monoid. Similarly here, we shouldn't be discarding any effects or any information when we would like to have a full monad. Alright, so that intuition gives us a guidance that probably we're going to have a semi-monad here and not a full monad, because we have to discard something. There's no way we can take into account all this information because we cannot combine G's. So let's just arbitrarily decide to discard the second effect. And that means we will basically ignore the second part of the tuple that the function f produces. So ignoring the first effect would mean that we ignore this. Ignoring the second effect means that we ignore this. So let's just arbitrarily decide that we will want to ignore the second effect. So that means we define a function f1, so the first part of f, which is this. So this will apply f and then apply the extraction of the first element of the tuple, which is then basically means we discard this. And then we get the function a to b. And now we just apply this map function that we had before to fa, and we get this result. So this is the same code as was above here. So this is one way of defining a semi-monad, which is we arbitrarily decided that we want to discard the second effect. We would have decided that we could have decided to discard the first effect instead. Would be also a semi-monad, and to show this is one of the exercises. So let's continue. Now let's take care of the case when G equals unit, and then we just have the identity function. Identity functor. Now this is also the identity monad, because we just define all the functions as identity. Flat map, f map, flatten is identity, pure is identity, everything is identity. And then obviously all monad laws will trivially hold, because all these laws mean composition of some identity with identity which should be equal to identity, so it's always going to hold all laws if you define all your functions as identity functions. So for this functor, you can define all your methods as identity functions, and that's what we do. And that's called the identity monad. Not a very interesting monad per se, but it's interesting to note that it is a monad. So for instance, this is a functor, also not a very interesting one, but it's important to have that functor as an example, because, for instance, in a construction, you use an arbitrary functor or an arbitrary monad, and you can substitute identity functor or identity monad into some constructions, like one of these constructions that have arbitrary functors or monads in them, and you get an example of a new monad by that. So identity monads and identity functors are not necessarily useless, not necessarily useful directly, but they are useful for constructing new monads sometimes. Let's now go on to verify the associativity law for the semi-monad that we found. So for brevity, we will define type aliases. So f is this. But you see, this is not a f is not a functor by itself. It has two type parameters. So it is a type constructor that has two type parameters. A functor should be a type constructor with one type parameter. So we need to write things with a kind projector, as we did here, in order to get the right syntax for a functor type constructor or a monad type constructor. But just for brevity, we're going to introduce this notation. These are type aliases. So this is f of GA, which is the what we denoted there as FA. Here it is explicitly taking G as a parameter. Now FF is just f of f. This is just the same as f of A. If we stop writing G, then that's what it will be. So, and this is f of A. Writing it out would be quite cumbersome, so I just want to introduce these type aliases. Now, in order to check the laws, the easiest way is to look at the flatten function, not the flat map function. So let's derive the flatten function from the definition of the flat map that we were given above. So we're given this definition of flat map, and flatten is flat map of identity, and the identity must be of this type. So let's copy this code and substitute identity instead of f. So that's what we get. Now f1 is a simple function that just takes the first value of a tuple. So we can substitute that into the code. So let's see. I'm going to rename this to FA and this to GFA, because the types of these things are FA and GFA. Remember that this FFA is of type FF of GA, which is this. So it's a tuple of F and G of F. So therefore I choose the names here, FA, GFA. These names were just copied from above. So I want to rename for clarity to remind myself what types these variables are. So now if you say here, for example, F1 of A, but F1 is just taking the first element. So instead of this, I write this. And here I write this. So let's further simplify. Now, obviously, FA is FFA dot underscore 1. So then this is dot underscore 1 dot underscore 1. And this is FFA dot underscore 2 map underscore underscore 1. All right, so this is the code of the function Flatten. Now, this is what I call a symbolic derivation of the code. So this code was derived by substituting function definitions and simplifying. But simplifying is more or less like in algebra. You have an expression, you substitute a function into it, and for example, here FA is f of a dot underscore 1, and so you substitute here instead of FA. So this is quite similar to mathematical derivations in algebra. So you just substitute equal values for equal values anywhere and substitute definition of functions to apply them and then simplify and so on. And so this is a symbolic derivation of the code. I could have just written this as a definition of Flatten. This would not be a symbolic derivation because I don't get the code of the function. I cannot reason about that code as easily. And here is the code of the function that I can later reason about. I can again do the same, substitute this and simplify. And that's what I will have to do in order to verify the laws. So there's this symbolic verification that I'm going to do, rather than, so to speak, a numerical verification. If I just wrote this and then used Scala check to call this function on 100 examples with integer types or something like that. Now, it will be certainly a bit helpful, perhaps, to do that. Unfortunately, in this example, we're trying to prove something for an arbitrary functor g. How are you going to do this with Scala check? I don't think you can do this with Scala check because there's no such thing as an arbitrary functor in it. I don't think so. It would be interesting to add that functionality, but it would be hard to do it just here in this tutorial. And this functionality, generating an arbitrary functor is kind of ambitious. So you probably need a lot of code for that. And so anyway, it would be hard to do, and it would only give you specific type parameters and specific functors checked, not arbitrary types and not an arbitrary functor. Whereas the symbolic computation that I'm doing here is more like a mathematical proof. It is rigorous. It is proving it correct for all type parameters and for all functors. Now, if you remember the associativity law for the semimonad, it involves fmap of Flatten. So we need to implement fmap. Let's do that. Fmap is just the same as map, what we did above, except its arguments are flipped. First comes the function f, and then comes f of a. Other than that, the code is identical. Now, the associativity law is that this expression is equal to this expression. So this function and this function are identical. That's the law. So in order to check that, we need to symbolically derive the code of these two functions and compare, and somehow show by simplifying, maybe renaming variables and such, that they have the same code, these two functions. So let's start by computing fmap of flatten, because that's the first function we need to check, is fmap of flatten followed by flatten. So that's, I just want to remind you, is the law of associativity. Let me find that slide. This is the law of flatten right here. Now, written in this short notation, this is a lifting in the functor, so this is fmap. So basically, fmap of flatten followed by flatten must be equal to flatten followed by flatten, with types accordingly matching. So let me go back to this slide and go back to my code. So first step, therefore, is to compute the code for this. So let's do it. So how do we do it? Well, I do it by writing out this function as if that were a separate function I'm defining. And the code for the body of this function will be symbolically derived. So I call this function fmap flatten. Just, it doesn't matter what I call it, really. I'm not going to call this function in the code. So I name this function just to be sure about what I'm computing. So this function, fmap of flatten, takes an argument of type fff of a and returns ff of a, because flatten takes f of a and returns f of a, and I'm lifting flatten once, so I'm adding one more layer of f. So in order to derive the code, let's take the code of fmap and substitute the function flatten instead of f into that code. So I take this, and instead of f, I write flatten. So that's what it's going to be. So it's going to be flatten of a, which is here called ffa because it's that type. And then it's going to be this map f, so this map flatten. So that's going to be the result of substituting the definition of fmap in here. So that's first step. So now let's substitute the definition of flatten, which was right here. Yeah, that was flatten. So let me keep it on the screen after we simplified it. So that was the code for flatten. So we need to apply this to FFA, and we need to do the, so FFA is instead of, yeah, FFA is right here, so we just repeat this in here, and the last part of the tuple is unchanged. So I put this all in comments because this is my preparation. Now FFA is the first part of FFFA, and GFFA is the second part. So then I rewrite it like this. So instead of FFA, I write FFFA1, and so on. So instead of GFFA, I write FFFA2, and so I get this expression, which is kind of a longer expression, but this is the code of this function, nested tuple. I have a double nested tuple, whatever. That's what I have to return. And the Scala compiler compiles this, and so that's how I check that I haven't made some trivial mistakes. So having compiled this, let us compile, having derived this part, let us now derive this entire thing symbolically. So again, I wrote a bunch of things in comments, which is how I derived it. So first step is to simply rewrite this notation in Scala. So rewriting this notation means you take FFFA, first you apply this to FFFA, and then you apply this to the result. So in other words, in Scala you would apply this to the result of applying this to FFFA, which is written up here. So I just copy it over here. So this is now after inside of Flatten, and after that we substitute the definition of Flatten. The definition of Flatten was up there. Let me look at it again. It's right here. So now I need to take that and apply that definition. So this 1, 1, for example, it would be just this, because this is the first tuple, and in the first tuple I take the first part, so that is FFA 1, 1, so this whole thing 1, 1, it is this, and so on. So I just apply these things, so I extract tuple parts from here, which is immediately possible. Notice here I didn't do anything with this FTN inside the map. I just keep it. Why? Because I can't do anything with it right now. I can't simplify anything in this part of the expression. It's under map, so I have no idea what it is acting on, and so I don't know what that is. I cannot simplify anymore. But later I will be able to simplify maybe. So I'll just keep it like that. All right, now we got this. So this, look, yeah, I still have this map Flatten with no simplification. However, now we can simplify because we have dot map of something, dot map of something else. We can combine the two maps, and that will be like that. So I just keep the first things unchanged, and here I combine. First I take Flatten of something, so I write out this function as FFA goes to something. FFA first goes to Flatten of FFA, and then I take the first element of that. So, however, now we can simplify, because Flatten followed by taking the first element is just this. Remember the code for Flatten, it was this. So the first element of Flatten is this. So then I can simplify, and this is my result. I could simplify this further, like that. At the risk of getting less readable, but we're not going to read this much more. Hopefully we get the second function now and have the same code, and we'll be done. We'll see how that goes. All right, so the second function we need to compute is this. This is the right-hand side of the associativity law. Let's do the same thing again. So we apply this to some arbitrary FFFA. And notice that the type of the return of this function is f. So flatten takes a triple f and flattens this twice and returns a single f. And here, map flatten did the same thing by first concatenating the inner layers, and this first concatenates the outer layers of f. So that's the associativity law, that combining triple f into f doesn't depend on the order in which you combine the layers of f. Alright, so let's continue. The first step is to substitute the definition of Flatten in here, And so now we have flatten of this. Let's again substitute the definition of flatten. Now for the outer flatten. So we take this, 1, 1, and so on. So once we figure that out, it's going to be this. I'm copying 1, 1, and then again the same, 2 map 1. Remember the code is take this FFA 1, 1, and then take it to map 1. So that's good. I'm just being very careful to make no mistakes, so I'm going slowly. Copying twice. Now let's simplify, right? This is a tuple. We can compute what it means to have 1, 1 of it. It's just this. So then we take that and we obtain this. So now we have again a situation with map. We can combine them into a single map, which is this. And voila, we have the same exact code of the functions. We just look at this code and we see they're the same expression. So this shows the associativity law for the semi-monad. Why can it not be a full monad? Well, mostly for the reason that you can't have a monoid if you discard information. But if you discard one of the arguments entirely. But more formally, I would say, for a full monad, we need to define pure. And pure must have this type. How do you define it? How do you get a value of g of a for arbitrary functor g? You can't. There's no way of doing that. Now, if you now say, well, maybe g is not an arbitrary functor, and maybe there is a function from a to g of a, well, that is already suspicious, because then maybe g is already itself a monad, or something like that. So for arbitrary functor g, certainly that won't work. We will have a construction 3 next, which is similar, where we have two monads, a tuple of two monads. So let us now go to example 3, and we'll show that a tuple of two monads or semimonads is again a monad or a semimonad. So here I'm preparing the type aliases first. Now it's going to be quite verbose because I have two arbitrary functors, g and h. And so how can I do anything with them? Well, let me just do this for brevity and define this notation. Now notice we have g of a tuple of g of a, h of a. So this is getting quite complicated. H of a tuple g of a, h of a. So we have g inside g, g inside h, and h inside g, and h inside h, which is kind of complicated. So how can we define a monad instance for this? So I'm not going to define flat map because it's much easier to define flatten. I did define flat map in the previous example, but then I had to define flatten. So why don't I just start with flatten? It's easier. Now, how do you define flatten? Now we have to somehow convert this into this. Imagine that we already know how to convert g of a into g of a, because g is a monad. h of A into h of A, because h is a monad, or semi-monad, let's say. But we have more than this. We have g of tuple g of A, h of A. So there's an h inside of g. How could we flatten that into g? H is an arbitrary type constructor. Well, it is a semi-monad or a monad, but there are so many different type constructors that fit that description, as we have already seen. It seems there's nothing else we could do here except to discard the h inside of g and to discard the g inside of h. Discarding it is easy because they're functors. So we can f-map or map this value with a function that takes the second part of the tuple or the first part of the tuple for this. We can just map like this, and that will discard those parts that we don't want. So it seems this is the only way we can solve this problem and implement flatten. Let's do it. So that's going to be the first part, map 1, flatten, so this flatten is in G, and the second part, map 2, flatten, that flatten is in H. Now we have, interestingly here, map followed by flatten. So here, map followed by flatten. This map is also in the functor H as this flatten. This map is in the functor G as this flatten. Therefore, we can combine map and flatten into a flat map. And we can write somewhat shorter code for this flatten function. Notice this flat map is in the first element of the tuple, which is the functor G. So this is the flat map of the semimonad G, whereas this is the flat map of the semimonad H. So there are two different flat maps really being used here to define this. All right, let's go on to define pure. That's much easier. We just take the pure of the monad G and the pure of the monad H and combine them into a tuple. We're done with writing the code for the monad. Now let's prove the laws. To prove the laws, we would need f-map. So what's the f-map? It's just a tuple of two f-maps. So here's a little bit of intuition about what this monad will do. So we have combined two monads into one. What does it give us? So here's an example. So actually, if you look at the flatten, you see only G and G are combined, only H and H are combined. So the cross terms, so to speak, H of G and G of H are just ignored. So that suggests if we write code like this, then there will be no interaction between the two parts of the tuple. So this will interact with this, and this will interact with that. So the result would be exactly the same as if we just split it into two monads and wrote two pieces of code separately, like this, and then combined the results in a tuple like that. So it's just exactly the same. So the result would be, for instance, here, if G is a monad, H is a monad, then you would just perform the for yield block separately for G and H and combine the results in a tuple. But you don't have to write it separately. You can write it like this. So this is shorter than writing this. So let's go on to the laws. The identity laws are easier to verify because the code is simpler. So let's start with those. There are two identity laws, the left identity and the right identity. Now, these are these two laws. So the first law means that the composition of these two functions is identity. So let's define this composition as a function called pure flatten. So again, I have to write all this parameter stuff. The type of this function is f to f. So yeah, go back to the slides and look at the laws just to see that we have done it right. So pure followed by flatten is identity, so this is this. So the type is SA to SA, or in our notation is FA to FA. And the right identity is also FA to FA. So that's what we will do now. Okay, so flatten of pure of FA. This is what it means. Because first we apply pure to some arbitrary FA of this type, and then we apply flatten to the result. Let's substitute the definition of pure, which is this. Now we have flatten of this. Substitute the definition of flatten, which is written here. This is the definition of flatten. So we just substitute it in there. And we take the first one, flat map 1, second one, flat map 2. Now, there's not much we can do with this expression anymore unless we remember that this and this are from monad H, and this are from monad G. And these monads must already satisfy the same law, which is that pure followed by flat map of some f is the same as applying f to this x. So let's use that law, and that means we need to apply this function to this fa, which means fa dot underscore 1, and similarly here. So the result is this. Now, fa is a tuple. So if you have a tuple of which you take the first part and the second part and then put them back together, you get the same tuple as you started with. So therefore, this is just identity function. And in this way, we've showed that the first law holds. So let's look at the second law. Similarly, we take the definition of what it means to have flat map pure followed by flatten. So you take some arbitrary FFA and you first apply fmap of pure of it, and then you apply flatten to the result. So let's substitute what it means. So basically, fmap works component by component on a tuple. So you need to do FFA1 map pure, FFA2 map pure. Then you substitute the definition of flatten, which gives you a flat map 1 and flat map 2 on each of these. Alright, so now we have this situation, we have map dot flat map. So this is in the functor G, and this is in the functor H. So we can use the naturality laws for these two functors, which we assume already hold. And if you look up what the naturality law is, it basically can interchange the order of map and flat map. That's what we do. So instead of this is a naturality law. Map f flat map g gives you a flat map f and then g. So if you do this, then you get, for example, flat map of pure and then this. So we have such expressions. But if you look at the definition of pure, it's monad G pure, comma monad H pure. And so the first part of this is monad G pure. So then we can simplify that. The result is going to be this. Again, we wouldn't be able to simplify here any further, except that we notice that this flat map is from the monad G. And so we have a flat map acting on the pure from the same monad. We can use the identity law for that monad, which means that this is identity function. And this is for the monad H, the identity function. And so the result is going to be FFA1 and then identity function. So we can just delete that. We get FFA1, FFA2. And that's exactly identical to just FFA. Something I just noticed is that the type here is FF and it should have been F. So why did everything compile? Well, because this FF type actually is just more restrictive than F. So we should have just changed this to F and things should still compile. Now I can rename this for clarity so that it's going to be consistent. So in this way we have symbolically verified the identity laws. Now let's verify the associativity law. And this is going to be a similar exercise in substituting function definitions and simplifying. Now notice that we have used the monad laws for G and H to derive the identity laws for the construction F, the tuple of G and H. But if G and H are only semimonads and not full monads, then we cannot use that. So we won't be able to derive pure either. We won't be able to derive the laws for the construction. So if these are just semimonads, then all the proof we have done so far does not apply. And we can only prove the semimonad for the resulting construction. On the other hand, in that proof, we don't need the full monad instances for G and H. We only need the semimonad laws and semimonad functions. We're not going to use pure for G and H. And so if G and H are semimonads, then the result will be a semimonad, and we are going to prove that now. So if we prove the associativity law, that's what we will prove. That semimonads give you a semimonad and full monads give you a full monad. And this is because in this proof now we're not going to use the pure functions from G and H. We're not going to use anything but associativity laws for G and H. So let's see how that goes. Again, we have to do two things. We have to compare that these two functions and show that they have the same code. So let's begin with this function. So flatten followed by flatten. I have written out the types for flatten, type parameters, just for clarity. Now, let's apply this function to an arbitrary FFFA of this type. So that means we first apply flatten to this function, and then we again apply flatten to the result. So flatten is this. So we apply flatten to the result. And the final expression is this. So applying flatten to something means that we have a tuple with _1 flat map _1 _2 flat map _2. So you do this twice. So that's what you get. And let's just leave it like this. We could simplify this because there is a composition of two flat maps, but it's not clear that this will help. So let's keep it here. The second function is the f-map of flatten followed by flatten. So that means we have f-map of flatten, applying it to FFFA, and then applying flatten to the result. So that's how it is. We again do the same, so applying to FFFA, you get the first part of FFFA mapping flatten. So that's, I'm just substituting the definition of f-map, which is up here, which is you take the first element of the tuple, apply the map, and you take the second element of the tuple, apply the map. Now these are two different maps. This is the map from the functor G, and this is the map from the functor H. So that's what you have to do. So that's what is here now. First map pure, sorry, I'm looking at the wrong thing here. First map flatten, second map flatten. Now let's substitute a definition of the outer flatten in here, which will add a flat map 1 to each part of the tuple and flat map 2 to the second part of the tuple. Now let's look at this. We can simplify, actually, because this is a map in the functor G. This is a flat map in the functor G, and there's a naturality law for flat map. So that law holds even for semi-monad G, because it's a law just involving flat map. We're not using pure for G anywhere. So now we can exchange like this using naturality. We do that and we get those things that we've done before. So flatten and then take first, flatten and then take second. So we do that, simplify to first flat map 1. So now we have this expression, flat map of first and flat map 1, flat map of second and flat map 2. So now we have a flat map of something with flat map inside. So that can be, now if you compare with what we have here, we don't have here flat map inside flat map. But the associativity law for the monads, if you look at the law for flat map, that's exactly what it does. It tells you that you can put flat map inside flat map or you can put it outside and the result is the same. So you can simplify like this. If you have flat map inside flat map, then you can just simplify it like this. And if we do that, we get that. So now this clearly line 208 and line 223 are identical. So since they're the same expression, the associativity law holds. So the next construction is, oh, I haven't shown this. So this is generally not a semi-monad, even if G and H are semi-monads. And the reason is, remember how we discarded the cross terms, the G of H and H of G. Now, you cannot do that with a disjunction. You can do that with a product, but not with a sum. Because if you want to implement flatten for this, then you would have to combine G of G plus H of G plus H into G plus H. But G of G plus H could just be G of H all the way. So there could be no G of G in it, because it's a disjunction. So it could be either one or the other. So G of H, G of G plus H is possible to be just of type G of 0 plus H, in other words, G of H. And you cannot flatten that in general. So that means this construction does not exist for disjunction of two monads. Disjunction of two monads is generally not a monad, not even a semi-monad. The next construction is that you take a fixed type R and you take a function from a fixed type R into a semi-monad G, or a monad G. I will not give a proof for this. I will leave this as an exercise. I will give proofs for most other constructions, and especially from the last construction, you'll see a similar kind of thing, but this I leave for you to prove. So let us now consider construction 5. Construction 5 is an interesting one, not often seen. Basically, it's making a new monad by disjunction with the type A itself. Now, we've seen that this is generally not a monad if you have here G and H, but if one of them is just the identity monad, then you can do it, it turns out. You need, however, a full monad for G. It does not work with a semi-monad G. So this construction is sometimes called a free-pointed functor over G. It's not important why it's called like this at this point, but we'll see later in a later tutorial when we talk about free constructions, such as free functor or free monad. This will be one of those free constructions where you construct a new functor with a new property out of a functor that doesn't have this property. Now, as I said, for this construction, G must actually be a full monad, so it must be pointed. Now, I remind you what pointed means. For a functor, pointed means a natural transformation from identity. In other words, a natural transformation of type A to G of A, which is the type of pure. So if a functor has a function with the same signature as pure, that's what it means that the functor is pointed. So let's, however, these are theoretical considerations. Let's go to the code that shows how to implement the monad instance for this and to prove that it is a lawful monad. So here I again prepare my type aliases for brevity. The type F is just an either of A and G of A. And FF is just F of F, and so on. Now, how do we define the monad or semi-monad instance? Well, the easiest way is to define flatten. In order to define flatten, we need to take this kind of value and return this. So this is an f of A written out in full, and this is an f of A. So how can we transform this into this? Now, given a disjunction means we could be given any part of it. We could be given just this, or just this, or this. And inside could be just this, or some combination, because this G is an arbitrary monad. So it could be a functor, a container having several values here of this type. So this could be one value on the left, one value on the right, and so on. So this could be complicated. So how do you return A plus G of A out of this? Now, if you are given this, then you can just return the same with no change. That is easy. But what if you're given this part of the disjunction? How do you extract a plus g of a out of that. Now that seems to be a little difficult. And the trick is that actually there is a function you can define which has this type, which I call merge. Well, I don't attach a lot of importance to the name of this function, merge. It's just for convenience. Let's call it merge. And this function can be defined. It's defined right here. I'll look at it in a second. Given that this function is defined, we can map this function over to the functor g and lift it into g. The result would be a function from g of this into g of a. So we have this function. And that function is what we need to transform this into, if we're given this part of the disjunction, into g of a. And now we can flatten the g of a into g of a, since g is a monad. And that's what is going to give us g of a, and we can return the right part of the disjunction, and we're done. How do we define the merge function? Well, that's a little interesting. If we're given the f of g of a, it means we're given this. So we're either given a or we're given g of a. We need to return g of a. Well, if we're given a, we use pure from the g, and we return g of a. And if we're given g of a, we just return that. So in defining this, we use the fact that pure is already defined for the monad g. This wouldn't be possible if g were a semi-monad. So the code for flatten follows more or less straightforwardly then. Flatten on the left of this is fa. So left of fa just returns that fa, which is this type. And the right of some gfa, again, I'm using variable names that conform to their type. You see the type is g of f of a. So if you have this, then we would have mapped with the merge and then flattened, which is flat map with merge. So we use that. That's how it works. So this flat map is giving you a g of b, and you put that g of b, in this case it's g of a, you put it into the right part of the disjunction here. So this disjunction is returned. So we're done. So this is the definition of flatten for the construction. The definition of pure is very easy, because if you have an a, you just return the left of that a. You don't actually use the pure of g to define this. But, as I have written here in the comment, the monad laws actually won't hold unless g is a full monad, and we have used pure to define flatten here. So we have used pure of g already, and that needs to satisfy the laws. The f map is standard, just f map for disjunction. If you have a left, apply f. If you have a right, apply f after map. Now, just a remark here. We have been able to define pure without using the pure function from g. And this is why this construction is called free-pointed. We were able to define the point or pure function, which is called point in some libraries, without, so for the constructed new functor, for this functor, we're able to define the point or pure function without using the point or pure function on this. And so that's why it's called free-pointed. So we we have information enough to construct the point function without already having been given this function before in the G. Now let's verify the laws. This is reasonably simple. The first law and the second law for pure are these. Let's begin with them. So first we have a pure and then apply flatten. So take some arbitrary FA, apply pure to it, and then apply flatten to the result. Now, pure of FA is just left of FA. That's the definition of pure. Now we flatten the left. When you flatten the left, it just gives you the value under the left. Therefore, flatten of left of FA is just FA. And that's the identity function as required. Now, F map of pure followed by flatten. That also has to be identity. Now let's do a F map of pure, applying it to some arbitrary FFA. I think I'm making again the same mistake as before. Let me check. Yes, this type must be F to F, not FF to FF. So let me rename. And this I also should have renamed. So now this must be of type G, yes. Good. All right, so let's go through this derivation. First, we substitute the definition of F map, which is this, where instead of the function F, we use pure. So we write this code, but we put pure instead of F. So that gives us this code. Now we can substitute the definition of outer flattened here, which is if you have a left, then you so you see flatten is applied to the result of this, which is either this or that. So we take these things and apply flatten to this, which will be that, and we apply flatten to this, which will be that, because the flatten of the right is a flat map merge. Alright, so now we have this code. Now we need to simplify. Well, what can we simplify here? Not obvious. Well, so they have this map and flat map, and these are in the monad G. So monad G must have its naturality law for flat map. So let's use that. So we have this law, and we use that law with F being equal to pure. And the result is going to be flat map of F and then G. So pure and then G. So pure and then merge is the same as pure. Now this pure is our pure that we are defining for F. It's not the pure for G. I always write explicitly this for the pure for G, because it is easy to get lost otherwise. So pure is not for G, it's for F. Now, if we substitute what it does, pure and then merge. So pure gives you a left of something, and merge of a left is a monad G pure of the content of the left. So that means we have a monad G pure. So pure and then merge is the same as monad G pure. So let's substitute it in there. So now we have this code. we have a flat map of monad G pure, and this flat map is in the monad G, as I'm reminded by the name of this variable, and I can check this also with IntelliJ. Sorry, I cannot check it because it's in the comment, so I can check it here. So this is of type. This I should have called this GA for less confusion, but it's just names of variables. Doesn't really matter what they are. But it's just helping to see what types they are. So flat map is in the monad G, and therefore we have a law. Flat map of pure is identity. So therefore we have this. And that is obviously identity. So this verifies the identity laws for the monad F. Now let's look at the associativity law. Oh yeah, and I never mentioned any naturality laws for monad F. We don't check them because the code already guarantees naturality. There's nothing in the code that uses specific types such as A being int or string or anything like this. The code is a composition of functions. It is substituting functions into arguments. It is completely natural in the sense of natural transformation. So any code like that is fully parametric. It uses functions such as flat map, which are already natural transformations by assumption, because they are in the monad G. So compositions of natural transformations or any kind of use of natural transformations will be natural. So we don't need to check naturality in any of this code. Any of these constructions are automatically satisfying naturality laws, but associativity law needs to be checked. So go on to check that law. To check that law, we need to compare this, so flatten of flatten, and this, flatten F map of flatten. Begin with flatten of flatten. So we apply flatten of flatten to some f of fa. So first we substitute the definition of flatten, which is this, and then we have the outer flatten on that. Substitute again the definition of outer flatten, which means that the left-hand sides stay, but the right-hand sides get a flatten applied to them. Let me check this, it's like that. So left f of a goes to flatten of f of a, and right g f of a goes into this. I can't simplify this anymore. Well, I could, like I said before, we could have a flat map dot flat map that could be simplified into a flat map of merge and flat map of merge. I'm not sure that will help any right now, so I'll keep this code as it is and look at the other one. Maybe we'll see what we need to simplify if we need to. So the other code. First, so I define this function, which is, I don't do it now by steps, this first and then that. I do it right away. So this function is going to compute that. So just f map of flatten applied to an arbitrary f of a, and then we apply flatten to that. So first we substitute the f map of flatten of f of a, which is this. This is the definition of f map, where we put flatten instead of the function f. So now we have this flatten and also this flatten inside. Go on. Substitute the outer flatten. So that means we apply flatten to these right-hand side parts. So this we apply flatten to this. And we apply flatten to that. So flatten of the left something, is just that something. So the inner flatten still remains here. You see, I put type parameters explicitly so that Scala compiles, because if I remove this, it's red. Interesting, right? The types are correct, and just that Scala cannot infer them, cannot guess what the type parameters must be. And this is often the case. Also here I had to put it in. Now notice this outer flatten has been substituted already. This is the inner flatten that still remains. And this is also the inner flatten that still remains. So now, if we compare these two, the left case is already identical. So we don't have to worry about it anymore. The right case is not yet identical. It has this versus this. So let's continue. We need to show that these two are equal. It's easier if we just stop writing all this code and start just writing one smaller expression at a time. So in the last expression, we have a map and a flat map from the functor G. So let's combine them using the Naturality Law for G. And then we get this. Now let's substitute the definition of flatten and keep merge as it is. So we have merge applied to the result of flatten. So you see, this is just the code of flatten. If you get rid of merge here, then it's just going to be the definition of flatten. So now we can substitute the definition of merge. On the left, so merge of right, merge of, well, this we cannot simplify, but we can simplify it on the right. So merge of right, let's look at again the definition of merge, what it is. Merge of right is just the content of that right. So good. So it's just going to give you this. So that's the simplification we can do. So now let's compare. So we're supposed to compare these two functions. We have simplified the second one, and we got this expression. So let's compare. So now we seem to have a flat map on here of some larger function, and here we have two flat maps of merge. In order to compare them, it would be easy to merge these two flat maps together using Associativity Law, or combine them together here. And if we do that, we will then have to compare GFFA flat map of blah with GFFA of flat map of something else. And that would be a direct comparison. We can drop GFFA flat map and compare those things inside. So if we do that, basically we need to compare the two functions inside flat map, inside this construction. And this is fine because GFFA is an arbitrary function, sorry, an arbitrary value. And so if we show that these are the same, then obviously we will have proved associativity law. So then the result so far is that we need to prove that these two functions are the same. These are the functions inside the flat map. Let's take this function, substitute the definition of merge, and put a flat map. So if you delete this flat map, that would be just a definition of merge. and we have applied flat map on its result so far. Okay, now we need to compare this and this. The right cases are identical. The left cases are not immediately identical, but again we have here pure from monad G and the flat map of monad G. How do we know it's from monad G? Because it's the result of pure is a G of something. So that's going to be a flat map also in G. Therefore we can use the identity law for G, and that's just that function. So that's just going to be merge of FA, which is exactly this. So once you simplify this, you get this. Therefore, both cases are identical. So this finishes the proof of the associativity law for the functor F. Notice that we have used both the identity law for G when we did this combination, and we used the associativity law for G when we combine the two flat maps on the G. So G must be a full monad for associativity here to work. G also must be a full monad for identity laws to work. But this shows that unless G is a full monad, even associativity law would not hold for F. So it wouldn't be even a semi-monad unless G is a full monad. But if G is a full monad, then F is also a full monad. So therefore we have shown that this F is a full monad for G also being a full monad, and that's the only construction we can show. The next construction is this one. Now, it's a G, which is an arbitrary monad, applied to this type expression, which is kind of a linear function of a type A with coefficients Z and W, where Z is a fixed type, arbitrary type, and W is a monoid. So this is kind of a straightforward construction if you understand monad transformers, but I just mentioned this for people who already know. But if you don't know yet, then this is just a construction that can be shown to work. So let's see why that construction works. Now, I'm getting tired of writing up all these type parameters all over the place, like this. So I'm going to cut down on the boilerplate in the later part of this tutorial, and I'm going to just put these parameters up front. So I'm going to define all the code inside a function that already has these type parameters, and then inside I don't need to talk about these type parameters. This is just to cut down on the boilerplate. Alright, so now for this construction, what we need is to apply some arbitrary monad G to a type constructor, which is this, either of Z and tuple of W and A. And this allows us to use a type alias now to define these things, because G, Z, W, and so on are already defined as type parameters up here. Alright, now actually P is itself a monad. And that will be an exercise 9 to show. We have seen parts of P, so to speak. We have seen this is the writer monad, and we have seen the either monad. This is a combination of either and writer, and this is also a monad. Mathematically speaking, this is Z plus W times A. And so this is like a linear function of A, which is kind of a simple example of a monad. All right, now f map is defined in the obvious way. If you have a left of z, you don't change it. It remains left of z. If you have a right of tuple WA, then W doesn't change, you transform A. Now we can write a cats monad instance if we feel like it. Cats monad is my own type class that has flat map and pure, and that can automatically export your monad into cats. How to define flat map? Well, this is a little maybe complicated, but it's really straightforward. For P, you don't do anything with the left, and then you map on the right, because on the right you have an A, so you have some W1, A1, you take f of that, you get a P of B. Then you match that. If it's the left, then again you return the left. If it's the right, then now you have two W's that you combine using the semigroup, and you have a A2, which is actually a B. So it should not be called A2. Let me rename this. Let me call this B to be more clear. The pure function is defined clearly as a right of empty monoid value of W and the A that you're given. So that's clear. That's just like the writer monad and either monad combined. So the flatten defined for P, I'm writing this code here because we will need it for reasoning. So let's look at how it works. So we have this type expression, and we want to convert it into this. How do we do that? Well, if we have a z, so see, looking at this type expression means that we can have a z, or we can have a w times z, or we could have a w times a. Because this is just like school algebra. So you just expand parentheses and plus and times symbols distribute. So if you have a z, or if you have a w times z, you cannot possibly return an a. So you must return the z here. The other case is that you have w times w times a, so you can return an a, and you combine these two w's. So that's what this code does. Let me make this more consistent. Done. So we have flatten and fmap for P, which I explicitly defined as flatten P and fmap P, and I also defined flat map for P. Let's see how we can define the flat map, flatten, or something for F. Now for G, we already have flat map and everything. We just want names for them for convenience. So I define them here again with these names. I'm using already defined code from the Functor and the Monad type classes for G. So that's just for convenience, because we need to reason about these fmap G and flatmap G, and so we want to have these functions. But of course we can't reason about these much, because we don't know what these actually do. This is an arbitrary monad, So we don't know what code is inside these. All we know is the properties. So we know that this is a lawful monad or a semi-monad. So it's the same story again. We will see that to prove associativity, we don't need the pure from G, and we don't need the pure, we don't need the laws of identity for G. We only need associativity of G. And so if G is a semi-monad, this will be a semi-monad F. And if G is a full monad, then F will be also a full monad. The F map for F is defined by doing a functor map on the function that takes a functor P map, because that's just a composition of two functors. So F is defined as a composition of G and P. So it's a composition of two maps, map of map. But let's write down the short notation, which will be quite helpful. So F map F is F map G of F map F of F, or we can write it like this, which is shorter. And let's see if we use that in reasoning in a shorter way. So then we can define a functor instance for G. For F by composing functor instances. And we can define pure for F. So this is a pure for F. I should have probably called it pure F, just so that we are not confused. Let me do this. So pure for F is defined in the usual way. We take the pure of G and we apply that to this, which is the pure of P. Right, we defined pure of P in here. So pure of F is just pure G of pure P of A. Or pure F equals pure P followed by pure G. Just like F map is like this, pure is like this. Let's see if this will help us reason about it. So now the interesting part comes. We need to define flatten for this functor. So the functor F is G of P of A. And so flatten needs to transform F of A into F of A. So F of A is this. And we need to flatten it into just one G and one P. So we have two G's and two P's, and they're interleaved. So somehow we need to transform that, and we could transform this if we change the order here of P and G layers. If we could transform that into this type, then it would be easy. You just merge this, flatten this into one G, then you flatten that into one P, and you're done. So what you need is to define this so-called sequencing function, which changes the order in the sequence of applying functors. So it takes P of G of whatever and returns G of P of that. This function does not always exist for all kind of functors P and G. You won't be able to define in general such a function. But this function will exist for a specific functor P, which is defined specifically by this type expression. So for this functor P, and for a few other such functors, this function will exist for, so this function changes the order, and let's define it now. How does it work? So it's supposed to take a PGC and return this. So, well, P is an either. The only thing we can do is to match. So what is the result of matching? If we have a left of Z, then we should return a G of something. Well, the only thing we can do, obviously, is use the pure of G to return a left of Z, because there's no way for us to return any A's or W's in this case. If we are in the right, then we have a G, actually, and we have a W. So let's see what we can do with this. We can take this GC and map over it. And we can add the W to that C that's inside it. The result will be a tuple of WC. We could put it into the right, and that would be of type P of C. And so now we have G of P of C, exactly as we need. So this is a little involved, but that is a very important function. Without that kind of function, there's no hope to define this construction for a composition of two functors being a monad. So seek, this function seek, is a transformation between functors P of G and G of P. And since it only uses natural transformations and fully generic code, fully parametric type. So C is anything. We don't use any information about what C is. Then it's a natural transformation. We don't need to verify the naturality law. And this is a naturality law. The functor on the left is P of G, and the functor on the right is G of P. And so F maps must be in the first functor and F maps in the second functor. That's a naturality law that exchanges the order of F map and your natural transformation. So I'm not going to verify this because of the parametricity theorem, but it could be done very easily, of course, in the same way as we verify all these other laws. You just write down the code of F map P, F map G, and so on, and you transform and substitute and simplify, and you get that these two functions have exactly the same source code. And so that's just a waste of time to do that because the parametricity theorem guarantees naturality. But you could do it. So now let's define flatten for F. We define it like this. We do it's a monad G. Flat maps, it's a flat map from G. Which takes a function of a complicated type. So let's look carefully at what that does. We're supposed to do f of A. Now f of A is actually G of P of G of P of A. And if we flat map with something, then this something must be of type P of G of P of A going to something. So therefore the inner function must take P of G of P of A and return something. Well, what should it return? Well, it should return G of something, because that's what flat map does. Flat map takes a function from some x into some G of y, and the result will be G of y. Now the result must be this. Therefore, this function, this inner function that we are not yet ready to write, this function must take this type and finally return that type. So I'm showing how I got this, how I derived it. You see, I'm completely looking at types and I'm not guessing. I'm just saying flat map must take that type, and that's what it should be, and it should return that type in order to return this. Now, how do we get from here to here? Well, obviously, we use the seek, which will interchange P and G into G and P. So that will be this. And then we flatten P. But flattening of P must be done under a layer of G. So therefore, it is fmap G of flatten P. And once we do that, we're done. So therefore, the type of this inner function must be this, and G of a flat map of that type would be a function of this type, exactly as we need. Take some time to check this so that the types are correct. The flat map has the right type parameters, and once you have checked it, you will see why it must be like this. But this is flat map must have that signature, G of x going to G of y, having a function x to G of y as an argument. And so x is this, y is this, and then everything works. So finally, this is the code. I'm just writing what I have seen, what I have done here. Seek and then fmap G of flatten P. So this little piece of syntax is necessary for Scala for some reason. I think it won't compile. I had trouble compiling it without this, but this is basically saying that this is a function. The seek is a function. It says unnecessary parentheses, but let's put them in for clarity. All right, now the short notation for this function would be useful for reasoning is that I take flat map in the G monad of this composition. And you can use naturality for flat map G to rewrite it like this. So now, actually, we are in a very good shape. We don't need to write code because the short notation works well enough. Now, in the previous examples, I didn't do this, and I wrote code. But let me try to avoid writing code. I could do the same as I did before, just keep rewriting the code. But let me see if the short notation works. Maybe it will work up to a point. All right, so in order to verify the associativity law, we need to verify that this is equal to this. So let's verify that. Fmap f of flatten f followed by flatten f. So we just substitute this definition of fmap f, which is this, and then substitute the definition of flatten f, which is this. Flat map G of seek followed by fmap G of flatten P. So I just put it in here and put it in here. And here I now look and try to simplify these things. So how do we actually simplify anything like this? This looks very complicated. The way to do it is to try to understand what parts of these things belong together to be simplified. So for example, fmap G and flm G, they can be manipulated because they're in the same functor, and there's naturality law that interchanges flat map and fmap. Or flatten and fmap. It has a naturality law, but only in the same functor. So flat map P does not have any naturality law with fmap G. So we have to pull these things together somehow in order to simplify anything. So, for example, I want to use naturality of seek. How can I use it? The only way I can use it is when I have fmap P of fmap G of some f immediately before seek. And here I have, what do I have? Well, I have seek here and seek here, and nothing is immediately before it. So somehow I want to pull this thing together so that it's immediately before seek, and then I can achieve maybe some simplification using naturality for seek. So how do I pull that together? Well, I have this thing, fmap of this. So let's see if we can first use this naturality, which is fmap G of something and FLMG of something else. So here's at higher level we have fmap G of all this and FLMG of this. So how do we pull this together? We use this naturality law and we apply this law and we get FLMG of a big thing. So that's the first step. So inside it is going to be all this stuff without the second FLMG, because the second FLMG is going to be out. So the result is that we have one big FLMG, so by combining this and this. I think I'm missing a parenthesis here somewhere, just to be completely pedantic. 1, 2, 3, 2, 3, 2, 1, 0. That's right. All right, so now we have combined this fmap G and FLMG into one big FLMG. The result is this. FLMG of this. So now, does this look like seek of, and to the left of seek, I have fmap P, fmap G of something. Does it look like that? To the left of seek, I have fmap G of something, but fmap P is over there. It needs to be immediately here, below, to the left of this. So how do I get that? Well, fmap we can split. So fmap of composition is fmap of this followed by fmap of that. So we can split that in the functor P. The result is this. Fmap P, seek, fmap G. Great. Now this is what we wanted. We wanted to pull together seek and fmap P of fmap G of whatever. And now we can pull this on the other side of seek by using naturality of seek. So naturality of seek is this law. And using this law, we pull it on the other side of seek. And also it exchanges the order of fmap G and P. But that's okay. So the result is this. Now let's examine this. We have fmap G, fmap G. Let's pull them together maybe. We get an fmap G of this. Now This is associativity law for P. It's equal to just flatten P followed by flatten P. So this is associativity law for flatten P. The result is therefore this. Now let's pull it apart, and we get f map G under FLMG. So then we can pull that out, maybe. It's not clear that this will help, but let's just see if that helps, because we still haven't seen the other expression. So maybe the other expression will be similar to this. All right, so at this point, there's nothing else we could usefully simplify. Let's look at the other expression. The other expression is this. So we substitute the definition of flatten f, and we get this. So now, how can we compare this code and this code? Well, both of them end in the same way. That's good. But this part is one big flat map, and this part is flat map, f map, flat map. So we need to combine this into one big flat map. Let's do that. By using naturality and associativity of G, we can do that. So naturality allows me to pull this inside the flat map, which gives me that. Associativity allows me to pull the second flat map inside the first flat map, which gives me this. So the result is one big flat map with this, followed by this piece, which is the same as that. So don't need to compare it, except for what's inside the big flat maps. And both of these functions have the same type, and look at the types. They're quite complicated, but I just want to write down what we had here. F map seq. Where is this? Yeah, here. F map P, flat map G of seq, followed by seq, followed by this. So I just write down Scala code for this in order to make sure that everything is still type checked and correct. So this is that. Now, a short remark here about notation. All these computations I've done here, I've never mentioned any types, as if the types will always match whatever I do. Why is this? Why don't I need to check at every step that all these types are correct? No. The reason is that these functions are polymorphic. They will adapt types to each other. As long as types can match, they will adapt as necessary. Each of our laws is a fully polymorphic, fully parametric type function. And so if the argument type needs to be changed, it can be adapted automatically. It will never lead to a type mismatch. Whatever you substitute, if a function is equal to another, you substitute, maybe the type needs to be adapted. But it can be always adapted because there's always some most general type for which the laws hold, which is the way we usually write them. So for example, for this law, this goes from f of f of f of a to f of a. But a is completely arbitrary. And so as long as you put that into any expression, a might adapt to something because it's an arbitrary type. But adapting won't ever break any types. So the laws hold for the most general types compatible with these function signatures. And that's why we don't actually need to check any types while we do this kind of manipulation. So now let's see. Now these two functions, it's not obvious that they are the same. They're quite different. So first of all, it starts with seek with a different type parameter, and this is this seek under fmap p flmg. It's completely unclear whether this is the same, and it's probably not the same as this. You follow it by flatten p under fmap g, and here the flatten p fmap g is at the end. And so it's not obvious that these functions are the same. So let's maybe write the code for these functions, actually. Or maybe try to evaluate them on some values, because it's impossible to simplify these expressions further in order to show that they're equal. Simplify, what I mean is that it's impossible to simplify by using laws of flat map and fmap g symbolically like this and not actually getting inside the code of seek, for example. So these functions are equal, but only for the specific code of seek that we defined. So that's why we need to now go a little deeper into the code. So the arguments of these functions are p of something. Because of that, the argument can be either left of z or a right of that. So let's apply these two functions to a left of z. And then we apply to these functions to a right of this and see what happens. So if, say, x is left of z, if we substitute the definition of seek, then seek of left of z, where it is assumed to be of that type, of this type. So z, left of z is still of this type. Then the seek of it would be, by definition of seek, if you substitute into the code, it will be this. And flatten of it is just left of z. So you substitute flatten p, and you get that. And so if we try to evaluate f1, which is seek followed by fmap g of flatten p and followed by flatmap g of seek. So what happens? First, we do a seek, so we get a pure. Then we apply we apply a fmap g of flatten. So inside this pure, applying fmap means applying the function to this. So we apply flatten to this, we get left. And then we do a flat map of seek on pure. And fmap of seek on pure is just seek applied to this left of z, which is this. So seek of left of z is a monad p pure of left of z. F2, on the other hand, gives me a trivial result because this fmap doesn't change anything because I have a left of z, so fmap p is identity on that. So I have left of z, then I have seek, which gives me seek of left of z, which is this. And then I have fmap g again of flatten p, which is the same as what we just computed. And so it's both f1 and f2 evaluated on left of z will give me the same result. So that is the first case. Now let's look at the second case. That's going to be longer. If x is the right of this, then we need to compute seek of it, which is going to be that. After seek, we compute fmap g, And that means we're already inside map in the G functor. So we just add another map in the G functor. So we do that. And the result is we can combine the two maps into one. And first we apply this to some PGA, and then we put flatten P on top of that. So that's the function we get. Therefore, finally F1, so F1 is seek, then this, and then flat map of seek. So add that. We can put in map and flat map by naturality because they're both in the G functor, and then we get seek applied to that. So then that's the result. Now, this kind of thing is the result of f1 of x. Now, for f2 of x, we first compute flat map G of seek under f map P, which means that, well, for the functor P, f map maps the right, and it leaves W unchanged, and it maps the value of type A. So then we get this, and then we do a flat map of seek on that. Finally, we apply a seek. So let's go back to the definition. Yeah, so we have done this so far. We apply a seek to that, then we have to apply this. So let's take that. We apply, we're here. Apply seek to that. We get this. Finally, we apply fmap of flatten P to this. So then we just tack on dot map of flatten P, because this is all these flat maps, and maps, they're all in the G functor. So let's pull that into one flat map using naturality. We get this. So now the result is we have f2 and f1 of x computed. So f1 of x is this, f2 of x is that. Both of them have the form gpga.flatmap of blah. So we need to compare just those functions, this function body. Let's compare them. One is this, and the other is that. Now, it's kind of hard to compare this because PGA is arbitrary, W is arbitrary. What can we do? So let's pattern match on PGA. And, well, I should have written code maybe, but I'm lazy. Let's just substitute values and see if it's working better. So PGA is either left Z or is a right of this with some W2 and GA. If it's a left Z, then let's look at that. So flatten of this would give you a left Z. Well, it can't give you much else, right? It couldn't possibly give you a right of anything, because it doesn't. For the right, you need a W. So you have a left Z. So sequence of left Z is pure G of left Z, and so we have pure G of left Z as a result. For F2, we have, so we need to look at this function where PGA is a left Z. Now seek of left Z is pure G, and then pure G of left Z, you map whatever you want to map. The Z is not going to go anywhere. It's not going to change. So the result is this. So therefore, for the left, these two expressions are are the same. So now it remains to compare these two expressions if PGA is a right of something. So we compute that, and the result is that here we have the flattened P of right of this, and here we have to combine W and W2 using the semigroup operation. The sec of that is going to be equal to this, and for F2 we perform the similar computation, and we basically again have the same expression because the flattened P works like that. And that finishes our proof. So I tried to make it shorter. So part of the way I was just doing symbolic computation at the level of functors and monads with no specific code. So this would be general. But after this point, I could not continue the fully general computation. I had to put in the specific code for seek and flatten P. And so that's, at this point, maybe it will be shorter to just start writing code and compare the code for these two functions. But I found that if I first substituted left, it was very quick. And so I did it this way. The next construction is this one. It's a very important construction because it's a recursive functor, f, that's defined recursively. And it gives you a monad for any functor GA, and G does not have to be a monad itself. So this is the only construction here where we get a monad out of an arbitrary functor rather than out of an arbitrary another monad. And because you get a monad out of an arbitrary functor, so to speak, for free, remember it's called a free monad over G. I mentioned that there are constructions called free constructions that give you properties for free. Well, for free means you don't have these properties in the data that you are given, and you're just creating them in some way out of the structure of the new functor. But in a later tutorial, I will explain the free constructions in a more detailed presentation. So for now, it's just a name for this construction. So let's see how it works. Now, we have seen this construction in the examples, and this was the G-shaped tree functor. So the G-shaped tree, in other words, a tree with G-shaped branches. That's exactly this construction. So the tree has either a leaf with a single value of type A, or it has branches inside the functor G. So the functor G describes the shape of the branches, and under each branch there's another tree, again, of the same recursive shape. So let's see now how this works. We assume an arbitrary functor G. Let's see. I said yes. So it's any functor G. This functor doesn't have to be itself a monad. I define this function construction 7 just so that I have fewer things to type. Now, we can't define a type alias for this because it's recursive, so I have to define a case class with a type parameter. And that forces me to have a name for this inner part, but that's not going to be used much. So this is just A plus G of f of A. How do we define flatten and f-map? We've seen this before. It's the tree, the G-shaped tree. So f-map on the leaf is just a transformed leaf. F-map on a branch is the same f-map recursively applied to each value in the branch container. So G works as a container that may have one or more values, and that's the branching. If it has more than one value, then you have several branches. The flatten works by keeping leaves as they are. So if you have a tree of trees, and the leaf of the tree means you have just a single tree, you return that tree. If you have a branch, then you need a map of flatten. So this recursive case is going to be the same for all of these constructions. This code cannot be written otherwise. You have to map over this functor with a recursive call to the same function. So pure is defined by just returning a tree having a single leaf that carries that given value. Let us verify the laws. This is the identity, second identity law. We just substitute the definitions again. So to verify this law, we need to take some arbitrary FA, apply pure to it, and then apply flatten to that result. So that's flatten of pure of FA. Substitute the definition of pure, we get f of left of FA. Substitute the definition of flatten, that's FA. So that's identity. And let's compute f-map pure of flatten. But actually, it will be maybe helpful to compute flat map. Now, f-map of something followed by flatten is flat map by definition. So let's compute that function first. Flat map. So how do you do that? So it's flatten of f-map of f of some arbitrary fc. What's the definition of f-map? Is this matching with recursive match. And when we substitute the definition of flatten, which means that we apply flatten to these right-hand sides of this match. So this remains the same. The right-hand side is flattened. So flattening this gives you f of c. Flattening this gives you that. And we can replace f-map dot flatten, because this is map of this dot map of this, which is equal to dot map of this followed by this. And we can just replace that again by FLM, because that's the definition of FLM. And so that's going to be the code for FLM. See, again, just recursive case is always the same. We just use different functions under map. That's always the same. All right, so what is now FLM pure? FLM pure is this. FLM pure must be id. Apply this to arbitrary FA. Substitute the definition of FLM, which is this. Put an pure instead of f. And so then we get this. Now, pure of C is f of left of C by definition. So this first case is just identity by definition of pure. The right case is this. Now, if we have proved that it is identity on the leaf, now we have a recursive case. Now we cannot directly prove that it is identity because we don't know what that is. We haven't yet shown that the right case gives also identity. So we need to prove this by induction. And induction is on the structure of the tree. If we are in the leaf, we have proved that it is identity. If we are in the branches, and for each branch we already proved that this is identity, then we need to prove that it's identity here. In other words, we can assume that this is identity when we recursively call that function. Once we assume that, then it's obvious. It's just map identity. So this is f of right of g of c. And so that's clearly identity. So assuming inductive assumption, which is that this function is equal to identity on any of the subtrees, we can prove that it's equal to identity on the whole tree. And that's how all these proofs are going to go. For recursive functions, that's the only thing you can do. You assume that the recursive calls to your function already satisfy the property that you want. And then you prove, that's the inductive assumption, then you prove the step of the induction. All right, so this proves the identity laws. Let's now prove the associativity law. Associativity law, which is this. Now, let's write down the code for these functions. Apply this function to an arbitrary FFFA of this type. Substitute the definitions, we get this. So the left case is that, the right case is kind of complicated. So we can substitute this into the first map, so then it will be flatten followed by flatten, which is the same as this function. So now we can therefore write the code like this. So you see, all of these functions are always going to have the right case using exactly the same code. So that's kind of a boilerplate, isn't it? There is a way of getting rid of this, but it's more advanced, and these are called recursion schemes. And I'll talk about this in a different tutorial. But for now, we will just keep writing this boilerplate. Each function will have a second case of this sort. Now, flat map flatten is the second function we need to compare with this one. We have substituted again flat map instead of this composition. So flat map of flatten applied to an arbitrary FFFA. Let's substitute the definition of flat map, which is this, and then we get, if we rename FFA to instead of C, then we get the code that's exactly the same as this, except for the name of the function. And the recursive call is, of course, to the function name differently. So if we rename the function now, then we can't distinguish the two functions anymore. So it means that their code is identical. So this shows the associativity. We have not used any properties of G other than map. So all we have here is this map on G. We have not used anything else. We have concatenated the two maps into a single map. That's a property of the functor, the composition law. We have not used any other laws for G. And so therefore, indeed we have produced a monad out of an arbitrary functor G. The next two constructions are, in general, only semi-monad constructions, so they do not yield full monads. The first such construction is the G-shaped leaf and G-shaped branch tree, which we have seen before. So leaves are of shape G and the branches are also of shape G. That's a tree like this, but we'll see it cannot be made a full monad, only a semi-monad. So let's look at this construction. We'll show that it is not a monad. So how? Well, let's define first. So we define, again, a case class with a type parameter. It's a recursive type because it uses f inside itself. So it's an either leaf, so we have G, functor G describing the leaf, and the functor G describing the branches. Imagine that G is a pair of AA. Then this will be a leaf consisting of two values of A, and this will be two branches, f of A, consisting of two new trees. So that's either two values or two new trees. That's the shape of this tree. So the flatten can be defined, certainly, and by redistributing leaves into branches. So if you're on the left and you have these leaves, then you just, these are leaves, so you have G of f of A, so this is of type G of f of A, and that's what you need to return. You can return a right of that, and you are in here, you're in the right part of the either, and so you can just immediately return that. So essentially you're redistributing G leaves into G branches. You have this option because the tree has this shape. The right case is just a recursive case. It doesn't do anything. It just repeats the same operation on all the branches. Fmap, again, same thing. You map over the leaves and you do the same operation on all the branches. Now, I will leave it to exercise 15 to show that this is associative. The proof is somewhat similar to associativity of the ordinary tree, but I will show that you cannot make this into a full monad here. If we wanted to do that and we defined pure, well, we need obviously a method on G which makes you some value. Well, suppose you had one, maybe. You can always have a pure from the free construction. If you have any functor, say h, that doesn't have a pure, then you take an either of AH, and that has a pure, just a pure being left of A. So that's a free pointed construction. You can always you can always do that. So let's imagine that G has a pure method, whatever it is. Then we can generate G leaves by using that method, and we can define pure. We could also generate G branches like this by doing recursive call of the pure, but that's of course infinite recursion, so that's not great. That's not great at all. Or we could terminate that recursion at some point. For example, we can do a pure of A, which is this, the one-step pure, generating leaves, and we can put that into branches, into another pure. So it's pure of pure, basically. So it's kind of a two-step pure. You generate many branches, but each of these branches is a leaf itself. So you could do this. You could imagine defining pure in a number of ways. And none of this works. Here's why. We need to have this law, so flatten of pure needs to be identity on an arbitrary FA of type f of a. So flatten of pure, if we substitute the definition of pure, is like this. I'm substituting this definition, the first one, the most straightforward one. And the result is that flatten will redistribute the leaves into branches. And so the result of this is always going to be a right of something. There's no way this could be equal to FA for all FA. What if FA is a left? That's it. You can't do it. This is not going to be an identity function. Now, no matter how you implement pure, whatever pure returns, it could return left, it could return right. After flatten, you will get a f of right of something. So there's no hope that that could be an identity function, because it will never return an f of left of something. And it must do that for some FA, like let's say for this kind of FA. And so already we see that the left identity law cannot possibly hold for this tree, no matter how we implement pure. None of these implementations will ever work. All right, so I keep you busy with the exercise that will show associativity of this semi-monad, and only one construction is left. This construction is unusual because it gives you a monad out of an arbitrary contrafunctor, or a semi-monad out of an arbitrary contrafunctor and a functor. Now, similarly to this construction, a full monad is only obtained when G is absent. So this is a construction that gives a full monad. The reasons are different from those in the construction we have seen before, those in construction 2, where here you could have a monad where G is a monad, not just an arbitrary functor, but here you cannot have a monad, even if G is a monad. We will see how that works. To define this construction, we start with semi-monad. So we assume that G is an arbitrary functor, H is an arbitrary contrafunctor, and we define the type f as a function type going from H of A to the pair of A and G of A. We will have to define a functor instance for f. For this, it is convenient to define a functor instance for this type constructor, which I denote fmap AG, which is what we've seen before in the previous construction, in construction 2. This is the same type constructor. Now, fmap for f is defined like this. So, to define it, we need to take a function f going from A to B, an arbitrary value fa of type f of A, which is this function. So fa is this function, and we need to produce f of b, which is again this kind of function with b instead of a. So to produce that, we write a function expression starting with hb, and then we have to return here a tuple of b and g of b. We do that by using fmap ag that returns us a tuple B of G of B. And we apply that f map f on some tuple of A G of A, which we obtain by calling this function on an H of A. But how do we get an H of A when we have H of B? We use contramap on H of B using function f. So contramap goes in the other direction, takes a function A to B, and transforms H of B to H of A. So in this way, we obtain the correct type, and there's no other way of doing it. Now, how do we compute flatten? Well, we need to define a function that takes an arbitrary f of A and returns f of A. How do we define that? Well, to return f of A means to return a function of this type. So we start the code by taking an argument of type H of A, and we need to return now a tuple of AG of A. We have a function of this type. What we need is to return this tuple of AG of A right now. So clearly we have to call this function on something. There's nothing else we can do. We cannot just create a tuple of type AG of A out of no data. So we have to call this function, but on what argument? We need to get an argument of type H of f of A. In other words, of this type. And suppose we can do that, then we call f of A on this, we get a tuple of this kind. Well, then we could discard the second part of the tuple and we get our f of A as required. So it remains just to get somehow a value of this type. So how do we get a value of this type? Well, we actually have a value of H of A. So what we need is to produce H of f of A using H of A. Why using H of A? Because they have no other data at the moment. So let's think about this. So we can use contramap on H of A to get H of f of A, and the contramap would need a function of this type. Why contramap? There's nothing else we can do with H of A. H of A is a value of an arbitrary contrafunctor H. We don't know anything about it, and the only thing we can do is to use contramap on that contrafunctor. Notice we are trying to do nothing special with these types. We're not trying to match on types or use reflection to see what that H is. We just use information that is available, which is that H is a contrafunctor and G is a functor. And since we keep doing just that, the result will be a natural transformation. So we're not doing anything special with specific types. We're always fully generic in our type parameters. Okay, so how do we get the function of this type? Well, f of A going to A is a function that can be written like this. It takes f of A and produces an A. So how do we produce an A? Well, we must apply f of A to something to produce an A. F of A is this type. So we need to apply f of A to some H of A. And we have one, this one. So we apply f of A to H of A. We get a tuple AG of A. We take the first part of the tuple, and that's an A. So that's the function we need here, on which we use contramap. I write out the argument, the type of the argument of this function for contramap to compile, because if I don't, Scala will get confused. We're done with this, so we now have defined a value of type h of f of a. We can apply f of a to it and get this, and then we take the first part of the tuple, and that's an f. We apply that to HA, and we get what we need. So this is a bit convoluted, but this is the correct way, or the only actually way of doing this, of implementing the type of flat map. Now, let's think about this a little more and think about how we can simplify this flatten, not flat map. Well, this thing is a function that takes h of a and returns h of f of a. And it turns out that this is a function we will use repeatedly. So let's define this function separately with a name. I call it insert f because it inserts a layer of f inside a layer of h, which can be done with this specific type. I mean, this usually cannot be done like this. You cannot insert something into another type constructor arbitrarily, but it is done as we have seen with these types. So I just copy this piece of the code in here, and then I can write a definition of flatten in a shorter way as this. F of a, instead of h of a, I use this. So then it's clear this is a function of HA. So the argument of HA is used twice. And because of this, it's hard to rewrite it in a point-free style. Point-free style means we don't write arguments of functions, we just write function compositions. So if we didn't have this application, then I would be able to write it in a point-free style as ftn equals, so ftn takes f of a and the result is a function that takes HA, applies insert f first to HA. Let me write it in a nice way. I'm looking for the function composition symbol, this one. Let me copy it over there. So first we apply insert f to HA, then we apply f of a to HA, and then we apply the first element of the tuple extraction. But actually, this still has to be a function that needs to be applied to HA, and there's no nice way of writing that down. So can't really write in a fully point-free style. And also, a fully point-free style would be that ftn equals something, and not ftn of f of a equals something. And we can't do that, because f of a is used like this. Inside, it's very hard. Probably, you could invent notation for this. It will probably not be very useful for reasoning about it. So let's I'm not sure if anyone has invented notation for the point-free style for such things, and if so, It's probably not very useful for reasoning, but in the Haskell ecosystem, there is a tool called point-free that transforms functions into a point-free style. The result of that tool are not always illuminating. So we tried, we don't see much use of this, let's not do it. So we'll keep it in the code. Let's now verify the associativity law. So to verify the associativity, we need to compare this with this. So let's define the first function, which is the composition of flatten and flatten. This function takes an arbitrary f of a. First, it applies flatten to that, so which is a flatten with the type parameter f of a. I'm copying now the short definition of flatten, and I rename HA to HFA because that's the type of that. Other than that, it's the same code. Now I apply flatten to this code, which means I write again this expression, but instead of f of a, I take this function. So this function is applied to insert f of HA. So that means instead of this, I have insert f of HA. So instead of HFA, I have insert f of HA. So I just substitute, I write this, and instead of HFA, I write insert f of HA. So then the result is this. I have now insert f of HA and insert f of HA. Because I substituted HFA into here. The second function, well, there's nothing here we can simplify. So at this point, let's keep it this way. We'll see what we need to transform when we look at the second function. So the second function is flat map of ftn followed by ftn. So we take f of a, we first apply flat map of ftn to it, which is, sorry, not a flat map, it's f map. So f map of ftn is obtained by substituting the definition of f map, which is this. So we copy this code in here, and I just renamed HFA so that it's easier to substitute later. Now we apply ftn to it. We get ftn of that. I just copied here. Substitute the definition of ftn, which is the same as to substitute this into this expression. So we have HA goes to this. So this HA comes from the definition of ftn. So ftn returns a function that starts with HA and returns this. And instead of FFA, you insert the function to which you apply flatten. So the result is this. So this is instead of FFA in that code. If we do that, you get this. So now it looks like we can't do very much except try to substitute the definition of fmap AG. Now look, we have fmap AG of something dot underscore 1. So let's see what fmap AG does when we do underscore 1 after it. So actually this can be simplified. If we look at the definition of fmap AG, it returns a tuple. And so dot 1 of it is just this. In other words, applying f to the first part of AG. So that's what it is, applying f to the first part of AG. Now we can simplify fmap AG of this function instead of f and this instead of AG. So this is AG dot 1 to which we apply this function ftn instead of f. And then we still have to apply the result to HA. Now, you see I'm very careful. I'm just copying the code and inserting. I'm not checking any types, but actually I could. I just uncomment this and see if Scala complains. Well, it probably complains. Let's see what it complains about. Too many arguments. Oh yeah, because I have this thing. Let me comment this out. Right. This is not valid Scala syntax. Right, so this has the correct type, so I can comment it again, and I can restore the comments as they were before. So by just putting this into the Scala IntelliJ code, I check the types. That's how I did it. So each of these was type checked before I commented it out. So now it remains to substitute the definition of ftn. So we have ftn here as a shorter form with two arguments, ffa and ha. So that's just this. So we put this and substitute, instead of ffa, we substitute this, and ha is ha. So we just put that there and we get this. Now let's compare these two expressions. FFFA of something dot 1 of this dot 1 of that. So that dot 1 of blah is the common element here. FFFA of something is common element. So the only difference is these two pieces, the insf of insf and insf contramap flatten. So these two are different. So let's see if they can transform into each other if we put more effort. Both of these expressions have type h of f of a, because we insert twice here, and here we insert once, and then we contramap. So let's show that they're always equal, and then if we can show that, we're done. We show that these two expressions are always equal. So this one and this one. So it remains to compare these two. So let me define just functions that take HA and return this, and the other function will take HA and return that. Now, then I'll transform the code of these functions. I'm defining them just so that I can easily check types without repeating all that. So now the first function is this. Let's substitute the definition of insert f, and we get f of a of this underscore 1 of this underscore 1. Remind you the definition of insert f is HA contramap of this. So we do HA contramap of this, contramap of that, which can be contracted to a single contramap with composition of these two functions. So that's what I did here. I combine two contramap calls. And and the result is this. So we have this expression. Let's try to see what happens in the other one. We have this. Let's substitute the definition of insert f, which is this one. Now let's compose the two contramaps. So we need to compose in the opposite direction. So we first apply this function, and then we apply this function. And in this case, the first function is flatten, and the second function is this one, apply ha dot 1. So then we have this contramap. First we flatten, take some arbitrary f of a, flatten it first, and then apply this function to the result. So that results in this function. Then we substitute the definition of flatten, and that is this, the short definition. Oops. So now we can compare these two expressions, and we see that they are identical. Let me see, I can probably remove this. Yes, this type annotation I can remove, and I can just rewrite this for syntax, so then they are syntactically identical. So this shows that these two expressions are identical. So that concludes our proof of the associativity law. That's to say it's a semi-monad. The only thing we have used is the contramap property and the map property for G when we defined fmap AG. So fmap AG is used to define fmap for our type constructor f, and contramap is used to define flatten. So that's the only thing we used to define flatten and fmap for this type constructor. So then it becomes a semi-monad, and we have checked associativity. So now let's see if this can be defined into a full monad. We'll show that actually this cannot be done unless G of A is unit. So in other words, we can only done it in that way. How to show that? Well, first of all, how can we create a pure for this f? We need to take an a, and we need to return a function that takes h of a and returns a tuple of a and g of a. Well, how can we return a tuple of a and g of a? Well, we have an a. We need a g of a also. The contrafunctor h of a is of no help. It cannot give us any values of type a or of type g of a. So we must ignore that contrafunctor argument of type ha. We have to ignore that argument. And we return a tuple of a, and then we have to have some function like pure g of a that returns a g of a given an a. In other words, we need that function in order to define pure. Let's imagine we have that function. In other words, the functor g is pointed. That's what it means to have that function, a natural transformation with this type signature. So imagine that the functor g is pointed. Can we define a full monad for the type constructor f? Let's see. We can define pure with the right type signature, that's for sure. Let's check the laws. The identity laws is that pure followed by flatten is identity. So let's do that. Take an arbitrary fa, apply pure to it, and then apply flatten to the result. Let's substitute the definition of flatten, acting on pure, so that will be this. Now, pure of FA is something that returns a function that ignores its argument. So we can ignore this. And the first part of pure of FA of something is just FA. So therefore, this is HA going to FA of HA. So all this goes away. This returns HA. So this returns FA. So this becomes FA of HA. So now the code is like this. And the function taking HA and returning FA of HA is the same as the function FA. So we don't, well, we could rewrite this as simply FA. So that is the left identity law, so that holds. Let's take the right identity law. It's fmap pure and followed by flatten. So we take an arbitrary FA, we apply fmap pure to it, and then we apply flatten to the result. And let's write HA right here for simplicity. And so we will apply this to HA. Let's now transform this expression. We substitute of the definition of flatten FFA HA, where FFA is this. So that gives you this piece, followed by application to insef of HA dot 1 of HA. So that's that. Now let's substitute the definition of this in here, where F is pure A, FA is FA, and HB is this. So the result, I'm just going to take the code for fmap, which is up here. And substitute F and HB as I just described. So the result is this. So now we again have the situation of fmap AG of something dot underscore 1. So that can be simplified. We have a pure of whatever was here applied to this dot 1. So pure was the first argument of fmap AG. This was the second argument of fmap AG. So then we have this first argument applied to the second argument dot underscore 1. Now let's see what we can simplify here. Well, we need to substitute pure, and we need to substitute this. We already know that insert f of HA contramap. We already know we can simplify that. So let's do that. It's an HA contramap pure and then this function, which is insf. So we can combine them into one function, first applying pure and then applying that to the result. So that gives us this function. Now this can be further simplified because that's definition of pure. Taking dot 1 of this gives you just A. So then basically this is just an identity function. And applying contramap of identity function, so this is just identity function. Contramap of identity function is identity. So HA contramap of this is just HA. So therefore, we can simplify our expression by using that this is just HA. So then we have pure of A, FA of HA, dot 1, HA. We can simplify this further by inserting the definition of pure, which is the tuple of this and pure G of that. So now we have simplified this. We can't simplify anymore because we don't know what pure G does and we don't know what FA does and what HA is. So now let's compare. This has to be equal to FA of HA because this entire thing must be an identity function. So identity function takes FA and returns again FA. In other words, it must return a function that takes HA and applies FA to HA. So that's, we expect to see just this. Instead we see this tuple. What is that tuple? Well, this tuple has the first part from FA-HA. Now, FA of HA is itself a tuple. Let's check that. So FA of HA is of type A, G of A. So it's a tuple. And if this were equal to FA of HA, then this should have been FA of HA dot underscore 1, comma, FA of HA dot underscore 2. So instead of FA of HA dot underscore 2, we see this. How could these two things be equal? For arbitrary FA of HA. It's the same as to say that we have an arbitrary tuple of this type, and the second element of that tuple must be equal to pure G of the first element of that tuple. So the function pure G must somehow be able to compute the second element of an arbitrary tuple from the first element. That's impossible. A tuple of two elements contains information in both elements. So this could be some arbitrary value of type A, and this could be some arbitrary value of type G of A. There's no possible way to compute the second value from the first in general, as long as the second value contains any non-trivial information. As long as it has more than one different value. We couldn't possibly guess what that value is, given some other value, unrelated to it. It's unrelated because we don't know what, there's no constraint on the function FA. FA is an arbitrary function that takes HA and gives a value of this type. So the function FA gives an arbitrary value of type A and then another value of type G of A. They're not related, these two. The type is like this, so this is G of A and it's the same A as here, but it's just the type. The values are not related. So it's, as long as the value of type G of A can be more than one different value, we cannot possibly guess or compute what it is. So it's impossible that this returns FA. Unless there's only one possible value in this type. In other words, G of A contains no information. There's only one value of this type, which means it's a unit type for all A. So G of A must be a trivial functor, constant functor that returns a unit type for all types A. So in that case, pure G is just a function that returns unit, and FA must have been a function that returns a unit in the second part of the tuple, and we're done. And it's the identity law would then hold. The first part of the tuple is fine. It's the second part of the tuple that's broken. So if G of A is unit, then the second part of the tuple is always unit, and both identity laws hold. So that completes the proof that this construction returns a full monad when GA is unit. In other words, when we don't have any GA, because we can simplify away product with unit into just A. So this completes the proof of all our constructions. Let me give a brief overview of what we have found. So first of all, these are not all possible constructions that give you a monad out of something. Certainly. You can combine these constructions and you are assured that you will get a monad as a result. But there are further constructions which I did not talk about, which I know, and probably there are also constructions that I don't know. There isn't, it seems, a theory in the literature that explains to you what are all possible constructions or what are all possible monads. That theory seems to be lacking in the literature. At least I couldn't find it. I did a search online. I made a question on Stack Overflow about this, but nobody seems to know. So for example, the question of how to recognize a semi-monad or a monad from its type expression, that seems to be an open question. In other words, nobody knows the answer. If I give you some arbitrary type expression, it's not clear that you can easily recognize that it's a monad or not. You can certainly try to implement the methods pure and flatten. There might be many implementations of these that fit the types, and then you would have to prove that laws hold. It's a lot of work for any given type expression. It could be a huge amount of computation that is not easy, and so there doesn't seem to be an easy criterion. However, if you can build a monad out of known constructions like these, you're guaranteed that laws hold, and so there's no need to check the laws. So these constructions give you examples of monads, such as a constant functor. So again, for a full monad you need a unit, but for semi-monad it can be just any type, fixed type. Then you have a product of A and something, which is a semi-monad only. A full monad only when the identity monad is considered, so G is 1. So these are examples. Constant monad, identity monad. Then you have a product of two monads, but not the disjunction, or sometimes the co-product as it is called. You have a function from a fixed type to a monad or semi-monad. Note that here you don't have a function from a fixed type to a monad. If this is a monad, that doesn't help to make that a monad. So recall we just proved that the identity laws cannot hold unless GA is actually equal to 1. So if GA is a monad itself, that doesn't help. It needs to be actually equal to 1 for this construction. For this construction, GA can be a monad, and then it's a product of identity monad and this monad, and the product works. So this is how it works. And here you can have a function from a fixed type to an arbitrary monad. Here, note, the fixed type is a contrafunctor. So this construction contains a fixed type as an option. So HA could be just some fixed type R. But the right-hand side must be of this form. It must be A if you want a full monad. So in this construction, it's a constant on the left, but this can be an arbitrary monad. This construction is a free-pointed, so it gives you another monad for a given monad. What does this construction do for you? If you already have the monad, why would you add A to it. The reason is this monad can be easily recognized as a value being pure or not pure. So in this monad, pure values are on the left, and any non-pure values are on the right. So any value that has an effect is on the right, and any value that doesn't have an effect is on the left. So I'm saying that a monadic value, or a value of a monadic type, has an effect when it is not a result of applying pure to something. So if it's equal to pure of something, then that monadic value has no effect, has empty effect in it. That's just an intuitive way of talking about it. It's not really that we can recognize the presence of an effect in a value, except for this monad. So in this monad, it's very easy to recognize the presence of an effect. If it's on the left, then there's no effect. It wasn't a result of pure. If it's on the right, then there is an effect. So for example, you start with pure, you apply some flat maps to it, you could get this. But if you just apply maps to it, then you would stay pure. And in this monad, it is easily recognizable if a value is pure or not. You can pattern match on the disjunction and find out. So maybe that is useful for certain applications, to be able to recognize by pattern matching whether a monadic value is pure, that is, has an empty effect, or it is not pure, has some non-empty effect. And also note, remember in the derivation of this, we had a function called merge, which takes this and returns g of a. So you can always merge this a back into the monad g. And that could be useful if monad g has some computational significance, and this is just some extra structure that you need temporarily for computation, and then you can get rid of it without losing any information. Merge it back. So that could be a useful structure. Now this is a monad where you substitute the type parameter for another monad, actually. We have seen, or you will see in an exercise, that this itself is a monad. It's a combination of writer monad and either monad. So this is now a combination of an arbitrary monad and this. Now this combination is interesting because it's a functor composition of two monads, of G and of this. And so this is an interesting example where a functor composition of two monads is again a monad. This is by no means always the case. But there are some monads, such as this one, such that a functor composition of an arbitrary monad G and this monad is again a monad. So that is important to know, that such monads exist, and this is a certain class of monad that have this property. Another class of monad that have a similar property is this. This is also a functor composition of the reader monad, R to A, and the G of A, but in the opposite order. So G of A is inside the reader monad, and here G of A is outside of this monad. So reader belongs to a different class of monads, such that their functor composition with any other monad inside is again a monad. But this would not be the case if you use this monad. If you put G instead of here, that would not work. So the reader monad and this linear polynomial monad are of different classes with respect to functor composition, that has relevance for monad transformers, which I will talk about in a later tutorial. Now this construction is very important. It's a free monad over a functor G, and it gives you a monad out of an arbitrary functor G. no restrictions on functor g. So this is used a lot to obtain monads out of arbitrary functors. Now, the last two constructions are somewhat peculiar. Haven't seen them in the literature much, or at all. I don't know if they have names, but so this construction is unfortunately only a semi-monad. It's a tree with G-shaped leaves and G-shaped branches. And this construction is interesting because it gives you a monad out of an arbitrary contrafunctor. Now, contrafunctors can be seen as type constructors that have a function in them that consumes some values of type A, let's say. A general contrafunctor can be a function from a functor to some constant type, let's say. A function from A to C, where C is a constant type. Or a function from a functor GA to Z, where Z is a constant type. So that's a general kind of contrafunctor of polynomial exponential class, of course. I don't know of any other way of reasoning about types except by talking about exponential polynomial types, that is, type expressions that have function type, disjunction, and conjunction, or product. So within this class of types, all contrafunctors can be seen as functions from some GA, let's say, to a constant type Z, say. And so an example of this would be arbitrary functor GA going to Z, all of that going to A. And that's a monad for arbitrary contrafunctor HA, or if you represent HA through another functor, then it will be a monad for an arbitrary functor HA, some GA. So this is another construction that gives you a monad out of an arbitrary functor or an arbitrary contrafunctor. I don't know yet what the use case is for those monads. There might be, but at this point, these are just the constructions that I found. And there are a few other constructions that come from monad transformers, but they are less general, and they all require monads. So there are no other constructions I know that take an arbitrary functor, which is itself not a monad, or an arbitrary contrafunctor, and make a monad out of that. These are these two constructions. And finally, I don't think there is any such thing as a contramonad, or a contrafunctor that is itself having a monadic property. I don't think that is possible because a contrafunctor such as HA consumes values of A. So A inside the contrafunctor are in the contravariant position. Now, a monad structure would mean that you transform H of A into H of A. But if H is a contrafunctor, then H of A is a functor. So because the two contravariant positions cancel each other. It's impossible to have a natural transformation between a contrafunctor and the functor. So there is no way that you could possibly have a function such as Flatten that takes f of A and returns f of A, where f is a contrafunctor. The contravariance here and here is different. There's no way to have a natural transformation between them, between a functor and a contrafunctor. And so there's no way for you to implement Flatten, and so there's no analog of contrafunctors that are monads in any way. Monads must always be functors. So this concludes the theoretical part. Now the exercises. Let me make some comments about the exercises. So the first exercise is to complete the proof that we started in the worked examples. We showed that this is a semigroup for a semimonad and semigroup S. But now if it's a full monad, you should show that this is a full monoid, given that S is itself a monoid, also a full monoid. The second exercise is a specific example of monoid, non-trivial monoid. This exercise is to show explicitly by symbolic code transformations that this is a semimonad. You have to implement fmap and flatten and pure. Notice here bool is a specific type, z is not, but this is bool. Bool is a monoid, so you can use any kind of monoid structure on bool. The next exercise is to show that this can be a semimonad but not a monad. Now notice this is actually equivalent to a disjunction of MA and MA, because Boolean is just two values, and so you can expand brackets and you get a disjunction. So MA, disjunction of MA and MA is not a monad. We know it's a semimonad because we have the construction, the product construction, but it's not a monad. So show that the laws don't hold. Next is again an exercise to showing that one of them is a monad, the other cannot be made into a semimonad. At this point, you see this is a reader monad, and we compose the reader monad and the writer monad. So we compose it in one order, first the reader and then apply the writer to that, or we first take the writer and then apply the reader to that. Now this is construction 4. So this can be made in a semimonad, but I did not prove construction 4, so you don't know that. Actually, it will be exercise 10 to verify construction 4. So for this exercise, just look at the types and see which one can have the type of flatten that we require. In other words, the type of flatten for this needs to be implemented. Can it be implemented? And can this be implemented? And if so, show one of them. I expect this one to be not a semimonad, because the type cannot be implemented. So similarly here, show that you cannot implement the type necessary for flat map or flatten, whatever you choose. Now, here P and Q are arbitrary and different types. You don't know anything about them. So for specific types, maybe you could implement a semimonad, but not for arbitrary types. In this exercise, you have this type constructor, which is just this. And you can implement flatten and pure for it. The types could be implemented, but the monad laws do not hold. So the exercise for you is to show that you can implement pure and you can implement flatten in many ways. So the exercise tells you to do it in at least 2 different ways, at least 2 different pure and at least 2 different flatten. But the laws never hold. Whatever combination of those implementations you take, the monad laws will not hold. At least some of them will fail. In this exercise, I don't expect you to enumerate all possible implementations of pure and flatten and check that for all combinations of these the laws fail, but this is so. There is a Stack Overflow question about it, which I initiated. Indeed, well, no, not I initiated. Somebody else actually had a comment on something I said in some other question, and they asked this question. So people have checked by explicit and full calculation, and I have checked it as well myself, that no implementation of pure and flatten for this type constructor will satisfy laws. So this is an example of a very simple type constructor, which is a functor, but not a monad, cannot be made into a monad for some obscure reasons. It's not obvious why, but something is missing in this type, and you cannot make a monad out of it. The next exercise is to check the laws now for functor, not a monad. The functor laws are what we discussed in chapter 4. So this type constructor is actually not a functor because it is not covariant. It contains an A in a covariant position and an A in a contravariant position. So this is actually not a functor, not a contrafunctor either. But for some obscure reason, you can implement a function fmap that has the correct type signature. This is the code for it. You should check that this has the right types. And so why is this possible? Well, this is just some kind of accident, but imagine that the programmer didn't think about covariance here and thought that this is my data type and I want fmap for it, and I can implement it. Great. Does that make this a functor? No, unless it satisfies the functor law. So the exercise is to show that it doesn't. The next exercise is to check the monad laws for this. This is similar to checking the monad laws for this, except now instead of bool, here you only verify the associativity, and here you need to verify everything, and W must be a monoid. Then in this exercise, this is actually one of the constructions, but the exercise is to write down implementations for flatten and pure explicitly and check the laws. Now, in this exercise, it's to show that pure, so the construction 5, let me look at it, what it is, yeah. So the construction 5 is this. In this construction, we defined pure for f as left of a. Now, the exercise here is to show that if we didn't, and we define it as right of monad G pure of A, which we could have done conceivably, because G is a monad, so we could put pure into the right part, into here. So show that if we did that, one of the identity laws would fail. So there's no way this would work. In the next exercise, the question is to take this and find the constructions that you can use to construct this monad. And once you find it, you already know that list is a monad, for example. You don't need to check the laws. So then you need to just implement the monad methods for it. And to do that, you look at the constructions, and the constructions actually implement the monad methods for each step of the construction. So you don't have to guess how to implement the monad here, because you have each step of the constructions showing you how to implement flatten given previous monads implementation. But of course, if you feel like guessing from scratch, then you can implement the monad method for this from scratch. In the next exercise is to try the construction 2, which was this one. In the worked examples I showed, I implemented this construction by discarding the second effect. In this exercise, you should repeat that but discard the first effect. So that would be a different implementation of a semimonad. And it's still a semimonad, so you should show that associativity is still satisfied. For construction 8, in the next exercise, I did not show that associativity holds. I just showed that it cannot be a monad, but I did not show that it cannot be a full monad, so it's still a semi-monad only. I did not show associativity, so you should show it in this exercise. And finally, in the last exercise, you should revisit the standard monads, the state and the continuation monads, from the first parts of the tutorial. We have verified the associativity laws for them, but not the identity laws. So this exercise is to verify the identity laws for them. Good luck with the exercises. This concludes it.